All right, Calc BC, we have this one page left. It's on trigonometric substitution. I'm going to talk about this right here, down here on this blank page, just for a minute. You've got these integrals, and look at them. This one has square root of 9 minus x squared in it. This one has square root of x squared plus 4 in it. All of these tables, a squared, the a is a constant, and of course x is your variable. So you either got a squared minus x squared, or you've got a squared plus x squared. Or the third type is, what if the x was first? X squared minus a squared. And of course these all have square roots in them. That's what this is about, the ones that are involving square roots. So what I would like to go over real quick before we do anything else, just so that we're all on the same page of what we're looking at. If you had a situation on a right triangle where, let's say that this side is x and this side is a, if we were using the Pythagorean theorem and we knew that this was our hypotenuse and we needed to find our hypotenuse, we know that our hypotenuse squared is our x squared plus our a squared. And if we took the square root of both sides, our hypotenuse then is the square root of x squared plus a squared. So this one I know ends up being, and it doesn't really matter if the x is here and the a is here. This also works if the a was here and the x is here. Okay, that's still going to be the square root of a squared, or x squared plus a squared. Okay, so this middle one is going to be, that would be your hypotenuse when they're being added, when you make your triangle, because that's what we're going to be doing. When we spot in an integral that we have the square root of a constant minus a variable squared, or a constant plus a variable squared, or a variable squared minus a constant, underneath a root, we're going to make a triangle, okay? So like I said, that one in the middle, that would be your hypotenuse on the triangle. And so then that brings us to, well, what if our hypotenuse was the x, okay? And in that case, this side is what I would be looking for. But the Pythagorean theorem says this, x squared equals a squared plus side squared. And so if I subtracted at a squared from both sides and then square rooted, this side becomes x squared minus a squared. So, you know, this x squared minus a squared, it would be a side on your triangle. And you'll see what I mean a little bit better whenever we get going. And it doesn't matter, it also holds true as long as your x is your hypotenuse. This could have been your a. This would have been your x squared minus a squared. Okay, so however the situation is. So that's the second situation. And then the last situation, what if your constant is your hypotenuse? What if this was your hypotenuse? And, you know, one of these was your sides. It doesn't matter which one. Well, if we were using Pythagorean theorem, a squared equals x squared plus side squared, we would say a squared minus x squared equals side squared, and take the square root of both sides. So you could see that this would become your a squared minus x squared. And, you know, the x could be here. This would also hold true as long as your hypotenuse stayed the same. Your x could be here, and your square root of a squared minus x squared could be there. So for the a squared minus x squared, it would be a side. This one is with hypotenuse a. This one was with hypotenuse x. But it really doesn't matter. I'm just trying to let you see and maybe understand it a little bit better before we start the problem. But anyway, so let's go ahead and look at the problem. I'm not worried about the rest of it. We'll talk about the rest of it in time. So this integral, if I was looking at this, I know that because they're being subtracted, it's a side, okay? And so if it was a side, and the one that I chose this one down here, 9 minus x squared, because I knew it was a side, and that would be like 3 squared. And remember, if your constant is here, that means your hypotenuse is your constant. And of course, this would just be x. Then you're just going to label an angle theta. And you're going to look at this and you're going to say, well, look, opposite hypotenuse. So the sine of theta is x over 3. 3 times the sine of theta is x. And then you're going to implicitly differentiate. So this would be 3 cosine theta d theta is dx. And so you come over here, and because you know what x stands for now, 3 sine theta, you're going to put that in. So square root of 9 minus, and instead of x, you're going to put 3 sine theta squared, and then over 3 sine theta squared, and then you're going to put your equivalency for dx in, which is 3 cosine theta d theta. So I put in my equivalency for x and my equivalency for dx based on that. And now let's just see what happens here as we start simplifying. So we've got the integral of, this is going to be square root of 9 minus 9 sine squared theta divided by 9 sine squared theta times 3 cosine theta d theta. Now you can say divide by 3, I get 1. Divide by 3, I get 3. Okay, so you can say that. We're also going to factor a 3 out of the numerator. So when we do that, we've got, a 9, sorry. We're going to factor a 9 out, but when it comes out as a square root of 9, which is a 3, sorry. So this is 1 minus sine squared theta over 3 sine squared theta times cosine theta times d theta. And of course, that square root of 9 and that 3 cancel because they are the same. So this is the integral. Now, 1 minus sine squared is cosine squared. So I'm going to put cosine squared there. And now, look, the square root and the square cancel. So I've got cosine theta times cosine theta, so that gives me cosine squared theta. And that takes care of this times this over sine squared theta d theta. And I know that cosine divided by sine is cotangent. So this is cotangent squared theta d theta. Now, I don't have a trig identity. I don't have a derivative that is equal to cotangent squared, but I do know a trig identity that I could use. I know that cotangent squared theta is equivalent to cosecant squared theta minus 1. So I'm going to replace that with cosecant squared theta minus 1. And I do know a derivative that is cosecant squared theta. So let's go ahead and just separate these. The integral of cosecant squared theta d theta minus the integral of 1 d theta. And this one is going to be negative cotangent theta, and then this would just be minus theta plus c. Now, I want my answer in terms of x. Bring this up over here. So my negative cotangent theta minus theta plus c, I'm going to go back to my triangle here. Cotangent of theta is this square root of 9 minus x squared here, divided by x. So negative square root of 9 minus x squared divided by x, that's negative cotangent theta, minus, now remember what my theta would be? It would be inverse sine of x over 3. Because if I had to solve this for theta, it would be inverse sine. So from here, I would get that theta is equal to, because that's my angle, is equal to the inverse sine of my ratio. And so minus inverse sine of x over 3 plus c. And that would be your answer for part A. Okay, so I don't know how to add another page. I would like to add a page. Let's see here. Oh, look, add page. Okay, so I'm going to take that next problem and put it on this next page. And the next problem for part B was the integral of 1 divided by x squared times the square root of x squared plus 4 dx. And again, you know, it has a square root, it has a constant and a variable, and this would be a hypotenuse because it's a plus. So if I drew my right triangle here, I know that this part right here is my hypotenuse. That means that this is x and this is 2, because this would be x squared plus 2 squared. So I've got my triangle now. I've got my theta. Look, opposite is my x, adjacent is my 2. So tangent of theta is the opposite over the adjacent. Multiply by 2 on both sides, and then implicitly differentiate. Dx, okay? Sorry, guys. Okay. Oh my gosh. Now you're going to put your equivalency for x in. And your equivalency for dx. Okay. Excuse me. I'm going to put that on top. This is going to be 4 tangent squared theta times the square root of 4 tangent squared theta plus 4. I know I know I can factor a 2, and I want to factor a 4 out of this underneath the root. So it's going to come out as the square root of 4. And the square root of 4 is 2 times 2, so there's going to be a 4 here. And the square root is going to end up being tangent squared theta plus 1. And when we go to a trig identity to look to see what tangent squared theta plus 1 is, it's secant squared theta. So our trig identity that we're using is tangent squared theta plus 1 equals secant squared theta. So we've got secant squared theta over 4 tangent squared theta times the square root of secant squared theta. So that's where we were going to put that trig identity. And look, the square root and the square cancel. And then one of these secants is going to go away with one up here. Right? So that secant is going to go away with that one up here. Simplifying it, integral secant theta over 4 tangent squared theta d theta. Now, if this were secant squared and tangent regular, you'd have a fine time, right? Because that would be the derivative. But since it's not, what we have to do is try to move everything into sine and cosine. That is what you need to do in a situation like that, because if you make your u tangent theta, it's going to be secant squared, and you're still going to have an extra secant. So what I want to do is I want to say, okay, this is 1 over the cosine divided by 4, and this would be sine squared theta over cosine squared theta. And we're going to try and simplify all that. And if you multiply by cosine squared theta over sine squared theta over itself, because you're wanting to get rid of this denominator, I guess I should have said 4 here, so that then you can see that this cosine goes away with one of these. So this becomes cosine theta over 4 sine squared theta. Now you can make your u sine theta. Now you can do the u substitution, because your du is going to be cosine theta d theta, and you'll solve for d theta. So this will be integral of cosine theta over 2 u squared du over cosine theta, and your cosine thetas cancel. So that leaves us with the integral. And I'm going to pull that 1/4 out front. 1 over u squared du. So really, we should bring that up like that, so that when we do add 1 to it, we've got 1/4, and then this would be u to the negative 2 plus 1 divided by negative 2 plus 1. And so negative 1 over 4u plus c, because that u needs to come down. So negative 1 over 4 sine theta plus c. And then we have to go back up to our triangle. What is sine theta? Well, sine theta is the opposite over the hypotenuse. That's x over the square root of x squared plus 4. So if we had negative 1 over 4 times x over the square root of x squared plus 4 plus c, this is going to become negative square root of x squared plus 4 divided by 4x plus c. Oops, sorry. It doesn't like me to write right there or something. There's c. So that is it. Oh my gosh. These problems are kind of lengthy. But, you know, you're looking for either the square root of a constant minus x squared, the square root of a constant plus x squared, or the square root of x squared minus a constant. If you have any of those situations, that's when you would draw the triangle, okay? And I think that's it for this lesson. Thank you.